For this example, we want to solve the initial value problem. dy dx is x squared plus 1 times y over y squared minus 4 with y of 1 equals 1. And look and see if there are any solutions that aren't of this form here. So let's start by trying to separate variables here. And if we do that, we will get that on the left side we have a y squared minus 4 over y times dy, moving all the y terms to the left, equals x squared plus 1 dx. And I can rewrite this integrand here, that's going to be integrand, on the left to give me y minus 4 over y dy equals x squared plus 1 dx. And now I can integrate both sides. So if I do that, I will get y squared over 2 minus 4 log of y equals x cubed over 3 plus x plus c. And again, we see here, I have a y that is outside a log and a y inside a log. There's no chance of trying to solve for y here, so we'll just leave it in this form and try to see what happens. So if I plug in my condition that y of 1 equals 1, I will get that 1/2 minus 4 log of 1, which is 0, equals 1/3 plus 1 plus c. So that term is gone. My c should then equal 1/2 minus 1 minus 1/3, which is minus 5/6. Therefore, the solution here is going to be y squared over 2 minus 4 log of y equals x cubed over 3 plus x minus 5/6. Now, what about solutions that are not of this form? Well, where does this form have problems? And I'm thinking about sort of this form here with that value of c in it. Now, are there any values here that cause problems? And it turns out there are. Y equals 0 causes some problems here. Because if y is 0, log of y is not defined, so this doesn't make any sense. So what's going to happen if y equals 0? Well, let's look back at the differential equation. If y equals 0, this is completely well defined, right? I can plug in y equals 0 and nothing breaks. But what we notice is that if y is 0, then the derivative is 0. If the derivative is 0, I have a horizontal tangent or a flat line, which means y doesn't change. So it turns out, based on this fact, that y of x equals 0 for all x is also a solution of this differential equation. And it is not of the form given here. You'd really have to look back at the actual equation and spot it, see what happens, or notice that this 4 over y has a problem at y equals 0. So maybe you should check and see if y equals 0 gives us anything that's more useful. So we also have the solution y of x equals 0, and this is what's called a singular solution of the problem because it doesn't fit the form of the normal expression. So we had these equations here that work for all sort of nice values of y, but there are certain values of y where it breaks, and at those we get these so-called singular solutions of the problem that don't match the normal form. And the way we're going to find these is by looking for sort of places where your general solution breaks down for values of x or y, and then seeing how those relate to what shows up in the actual equation in the beginning. That's an example of one of these separable equations that has a singular solution, as well as how you solve out again when you can't solve out for y in the first place.